Hi folks, we're going to take a look at number 12 from page 146. I'm actually only going to solve 12a. 12b is exactly the same, and we'll actually get a sense of what the conclusion might be based on our results from a. Okay, and I'm actually going to solve this in two different ways, just so I can show you some of the different tricks that that we have to solve these geometric problems. Okay, and my first approach is going to be a traditional geometric approach. So I'm going to start by drawing a diagram. So we have a rectangle that's inscribed in a right triangle with non-hypotenuse sides 5 and 12. Okay, and they specify that the sides have to lie along those legs, not surprisingly. So let me draw my triangle 5 and make this a little longer, 12. Okay. And inside here is inscribed a rectangle. Okay, and what I want to do is maximize the area. So I'm going to be working with A equals length times width. And as usual, we have a scenario where we've got two variables. All right. So the approach I'm going to use here, so this is the length and the width, is I'm going to use, like I said, a more traditional geometric approach. And I hope that when you look at a diagram like that, you can see some interesting things. In particular, we see a lot of similar triangles here. Okay, this triangle is similar to the large triangle, which is also similar to this triangle here. All right, and when we have similar triangles, we know that the ratio of corresponding sides is equal. Okay, so this is what I'm going to use to write this in terms of one variable. All right, so I definitely want to work with the big triangle because I know both the side lengths 5 and 12. So I'm going to do is I'm going to work with this smaller triangle up here, which shares all the same angles, hence similar. Okay, so I've got this side length of 12, which is going to be corresponding to this side length here, which I already know is L. Okay, and so I need something that's going to correspond with this side length of 5, and it's going to be this little portion here. So if the whole thing is 5 and this portion is W, this can be written as 5 minus W. Okay, and this is what I'm going to use to set up my proportion. Okay, so I'm going to start with the simpler one. I'm going to start with L. So this length here corresponds to the length of 12. So we have L over 12 is going to be equal to the ratio of these two side lengths. Okay, the ratio of 5 minus 12, 5 minus W to this side length of 5. All right, and so what this does is it gives me a relationship between L and W. So now you know something to look for in a geometry problem is to see if you have any similar shapes, in particular similar triangles that could be useful for you. Okay, and clearly here the easier one to isolate is L. So L can just be written, so I'll bring the 12 to the other side, so it's going to be 12 over 5 times 5 minus W. And now I can take this and input it into my equation, and I'm going to end up with only one variable. So L can be written as 12 over 5 times 5 minus W, and then times the width of W. And not only do I have a nice equation, it's quadratic. So I know showing that it has a maximum is going to be really easy. I should still specify my domain here. So here we know that W has to be greater than 0, and it can never be bigger than 5. Okay, it can get, as this thing gets really, really thin, the W is going to get larger, 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 but it can never be bigger than 5. So it's going to be greater than 0, but strictly less than 5. All right, so let me just simplify this here so I can take the derivative more easily. Definitely don't want to use the product rule here. So 12 over 5, and let's write this here as negative W squared, and then plus 5W. Okay, so now let's take the derivative. 12 over 5 is just a constant. Don't need to worry about that. So 12 over 5 times the derivative of this expression. So negative 2W plus 5. And of course, we're going to make that equal to 0. And solve for when this value is 0. So that's going to be W equals 5 over 2, which lies in my interval. Okay, and since it's a quadratic, I know that this has to be the absolute maximum. So here I'll say it's an absolute max. Okay, since the formula for area is quadratic, and the leading coefficient is negative. Okay, that's enough to guarantee that this value within the interval has to be the absolute maximum. Okay, so now that we have that established, let's see what they're looking for. They say determine the area of the largest rectangle. So now I can just take this 5 over 2 and input it into the area formula. So 12 over 5 times negative 5 over 2 squared plus 5 times 5 over 2. And I'm going to stick that into a calculator, make my life easier. Okay, although we certainly could do it by hand. So here, let me do the bracket first. So we have negative 5 over 2, which is 2.5 squared, plus 5 times 2.5. Okay, and then times 12 divided by 5. So times the 12.5 there, and we end up with 15. Okay, now I'm not going to do B, but maybe we can see if there's something interesting here. And I noticed that, well, the area here is 15. Why don't I compare it to the area of the original triangle? So if I take the, original triangle, well, what do we have? We have 5 times 12 divided by 2, and this 60 over 2 is equal to 30. Okay, and by the way, this is centimeters squared, and I see here that the area of this triangle is exactly half the area of the original triangle. Okay, interesting. I suspect if you do part B, you're going to see the exact same thing happening. And in fact, even though we don't have to find the length, I do notice that the width, 5 over 2, is exactly half of the length of this side of the triangle. And so if we find the, sorry, that was the width. So now if we find the length of this rectangle here, what do we have? We have 12 over 5. I'm just using this equation here. 5 minus 5 over, 5 minus 5 over 2. Tried to go too fast there. And of course, this is just going to be 5 over 2 because it's 5 minus 2.5. Okay. And what do we have? 6, which is exactly half of this length here. So it means that the largest rectangle is going to be the one where it hits the midpoint of the hypotenuse, which might have been a good hypothesis to begin with. If we had to pick one, that would have made sense. Okay, and I think you'll see that if you do it with that other triangle, you're going to get a very similar pattern. Okay, now, while this is all great, I do want to show you another option. Okay, and this is going to be an analytic geometry perspective. And what I mean by that is we're going to take this scenario and we're going to put on a Cartesian plane. And we're going to see that it's actually very similar to a question we've already solved. Okay, so I might have started this problem differently. I might have taken Cartesian plane and said, well, here's the point 0, 5, and here's the point 12, 0, and the triangle makes sense to have it lie on the x and y axes is here, and I have to draw a rectangle that's inscribed inside that triangle. So this is still my length and my width, except now I can relate everything to x's and y's. So I see the length, since I've put one side on the y-axis, is just going to be whatever the x value is at the end of this rectangle, and the width is just going to be the y value of this function here, which is just a line. Okay, so we did a similar one with an e to the minus x. This one's actually a little simpler, except they don't give us the equation. I'm going to have to find the equation of this line, but that's easy. It's an equation of a line. So let's start with the slope. I'm just going to use rise over run here. So as I move from left to right, the rise, it actually falls by -5 units. Okay, or it falls by 5 units, so -5, and the run is just 12. And I know that the y-intercept is just 5. So the equation here is just -5 over 12x plus 5. Nice and easy. Okay, so that means that the length is just given by x, and the width is just given by -5/12 x plus 5. So when I go to do my optimization, I'm still working with the area, which is equal to length times width, except the length is represented by the x value on the graph, and the width is represented by the equation of the line, -5/12 x plus 5. Now you might notice this equation is not the same as the one we had before, but that shouldn't be too surprising because here my variable was representing the width of the rectangle, whereas here now my variable represents the length of the rectangle. Okay, but it's just as easy a problem because this is just going to be, again, a quadratic function with a negative leading coefficient. Okay, here now my domain, well, x has to be greater than 0, and clearly x can't be greater than 12. So there we go. All right, so let's find our derivative. So this is negative 5 over 12 times 2x plus 5. Set our derivative equal to 0. So that simplifies a little. So negative 5 over 6x plus 5. So 5 over 6x equals 5. And so x is equal to 5 times 6 over 5. Okay, which is equal to 6. Which, if you remember from what we calculated earlier, was the length of the largest rectangle. Okay, let's put this into our equation. I have to make sure that this equation still gives me the correct answer that I got before. So negative 5 over 12 times 6 squared plus 5 times 6. All right, so let's calculate that here. So negative 5, whoops, let's turn it on. Negative 5 divided by 12 times 36. Okay, plus 5 times 6 is 30, and there we go. I get 15, which is again half the area of the original triangle. And if I calculate my width, I hopefully get 5 over 2. So negative 5 over 12 times x, which was 6, plus 5. So this reduces to negative 5 over 2 plus 5, which is 5 over 2. Okay, so I get the exact same answer. So this approach involves putting my shapes on a Cartesian plane and using equations of lines. This version here relied on geometric properties such as similar triangles. So the idea is to never do it both ways, okay? But what you have now is you have different options to work with. So especially if you're working with things like triangles, rectangles, things that are made up of lines, very easy to use an analytic geometry approach. Whereas if you're probably working with things like circles, you certainly can work on the Cartesian plane, but you might decide to stick with a more traditional geometric approach. Okay, that's it for this one.